Ma'am, we are not listening.
Ma'am, can you hear me? Ma'am, you are on mute. We cannot hear you.
ഓക്കെ, ഇപ്പൊ കേൾക്കുന്നില്ലേ? മൈക്ക് മ്യൂട്ടായി പോയി.
Yes, ma'am.
ഓക്കെ ഓക്കെ, താങ്ക് യു. ആ, സോറി, നിങ്ങൾ ഇപ്പോഴാണല്ലോ വിളിച്ചു ഒരാള്. ഒന്ന് ഇടയ്ക്ക് വിളിച്ചാൽ മതിയായിരുന്നു. Okay, I'll just quickly go through whatever I said earlier. എന്തായാലും നിങ്ങൾക്ക് മനസ്സിലായില്ലേ ഞാൻ ആദ്യം പറഞ്ഞത്? So whenever we are doing circular convolution, we need to make the length equal and then just do the convolution. It has no meaning. Okay. In the case of linear convolution, we will make the length equal to m plus n minus 1 and then do the convolution using multiplying the DFTs. Okay. And while multiplying the DFTs, or while we are finding the DFT itself, you can see the first value will be a DC component and the rest will have a conjugate symmetry. Even when you are finding the product of the DFTs also, you will have a symmetry. You will have to observe all these things. Okay. Then I hope we completed all these problems earlier. Computational complexity of DFT. Adana, that was what we were discussing. To compute a 4-point DFT, we need 4 into 4, that is 16 multiplications, 4 into 3, 12 additions. Okay. Now to do this 4-point, it's easy in the classroom level. To do an 8-point, you will need 64 multiplications and 56 additions. And as the value of n increases, then this is the figure that shows that as the value of n increases, n square becomes a very high number. Okay. So as we are either doing manually in the class, at least we should be able to do a 8-point DFT. And when you are using a system or a computer or a processor, DSP processor, and then if you are doing the DFT, still we need to reduce the time because we need quick response, okay, for our systems. So to overcome, how do we overcome this computational complexity? That's the question in front of us. So the solution is to use FFT algorithms. FFT algorithms fast Fourier transform algorithms. What is the use of this FFT algorithm? They are simply used to compute the DFT of any given sequence, can be computed using FFT algorithms. So these FFT algorithms exploit the symmetry of the spectrum. We already considered when we are drawing a spectrum, if you see, there will be a symmetry. For example, if the spectrum is to be in the center, okay, sorry. You have a symmetry. The left side and the right side will be the same. This is what we are going to exploit. So this, I think if we, I don't know whether we did it in the class. In the class, we will do it in the next day. Okay. So let's go into FFT. Just give me a moment. Okay, can you see the fast Fourier transform?
Yes, ma'am.
കേൾക്കുന്നുണ്ടോ ഞാൻ സംസാരിക്കുന്നത്?
Yes, ma'am.
Okay. What about the slides? Okay, അല്ലേ?
Clear, ma'am. Yeah.
Okay. Okay, let's see what is a fast Fourier transform. Fast Fourier transform is nothing but I hope you all read this statement. So fast Fourier transforms are just a set of algorithms formulated to compute the DFT with lesser number of computations. That is lesser number of multiplications and lesser number of
പിന്നെ stuck ആയിന്നാ തോന്നുന്നത്.
Hello?
പിന്നെയും പ്രോബ്ലം ആയി തോന്നുന്നത്. നമ്മുടെ സ്ക്രീൻ അനങ്ങുന്നില്ല.
Screen കാണുന്നില്ലേ? Okay, let me check. I'll just stop sharing and then I will again add. ഇപ്പൊ കാണുന്നുണ്ടോ?
Yes, ma'am.
Hello?
Yes.
Okay. So FFT is nothing but a set of algorithms formulated to compute DFT with lesser number of computations. Both FFT and DFT are the same. Okay. FFT is just computing the DFT in a faster way. That's all the difference. Okay. If you are asked to compute DFT, you can use FFT algorithm. Different types of FFT algorithms. We have two types of FFT algorithms. One is a radix decimation in time FFT algorithm, and the other one is decimation in frequency FFT algorithm. Okay. Then the algorithm is going to give the same outcome. Only thing is they have formulated two different algorithms just for the sake of clarity. Okay. And each decimation in time as well as decimation in frequency, they are further classified into radix 2, radix 3, radix 4, etc. Okay. And നമ്മുടെ syllabus we have only radix 2 algorithm. First I'll tell you what is a radix 2, radix 3, etc. Then we'll go into the actual algorithm. Okay. So what is a radix 2 algorithm? If the length of the given sequence whose DFT you want to find out is going to be a power of 2, okay, then we call it as a radix 2 algorithm. So if you have a length n is equal to 8, for example, 2 to the power of 3, you can see that you can keep on dividing these numbers until you get a 2. Okay, adana radix 2 in the specialty. Similarly, if you are going to use as a power of 3, then you will have radix 3 algorithm and so on. Okay, that is the meaning of this word radix 2. Out of this, we are going to see only radix 2 algorithm. Okay. And what is this decimation? Decimation is actually you are going to select, for example, if you decimate a sequence by 2, you are going to select every second value. If you have a decimation of in L, then you will select the Lth value. Okay. In signal processing, decimation by a factor L actually means keeping the Lth sample. Okay. So here decimation into 2 is actually keeping every second sample. So let's see how to formulate the radix 2 decimation in time FFT algorithm. So radix 2 decimation in time means that it is decimated in the time domain. Okay. Every second value is taken for this algorithm. Okay. Decimation in time FFT. So we are going to divide the sequence into 2 halves, or the DFT summation, that is number. What is the DFT summation? N is equal to 0 to n minus 1 x of n into Wn of nk. Number DFT. This has actually totally how many values? N value. N elements are there in the summation. N terms are there in the summation, right? So we are summation can be done in any way, right? You can add 1 plus first term, second term, third term, or you can add the first half, then the second half, then add them together. Here what we are doing is we are going to take the even terms and the odd terms separately and then add them together. Okay. So we are going to divide the two sequences. That is the even part. Xe of n will take only the elements x0, x2, and so on. And the odd part, xo of n, will take only the odd parts, x1, x3, like that. So we call this even part of the sequence as x1 of n and the odd part as x2 of n. Like this. X1 of n will have only the even parts, x2 of n will have only the odd parts. Okay. That means odd samples of the sequence and even samples of the sequence. And then we can write like this. DFT of x of n can be written as DFT of x1 of n plus DFT of x2 of n. Yes. That is like this. Okay. So how many elements will you have in this summation? Since we have already expressed n as a power of 2, half of n will be there in each of the summation. So this has n by 2 terms and this has n by 2 terms. Okay. Now how do we represent the even part? We can represent the even part as x of 2n and the odd part as 2n plus 1. Okay. So 0 to n by 2 minus 1 x of 2n into wn of wherever we had an n, we have replaced it with 2n. Okay. For the even part. And then wherever we had a odd one, we are replacing it with 2n plus 1. And here also 2n plus 1. Okay. Is this clear? So now we already gave a name, right? x1 of n is the even part and x2 of n is the odd part. So we'll replace it with x1 of n and x2 of n. Okay, next what we are going to do is we are going to simplify these two terms because Wn of 2nk can also be written as, what is this actually? This is equal to, first we'll write Wn of nk is equal to e to the power of minus 2 pi by n into nk. So now Wn of 2nk will be what? E to the power of minus j 2 pi by n into 2nk. This 2 can be brought to the denominator, okay, like this, e to the power of minus j 2 pi by n by 2 into nk. Then now what is the standard way to write this? This can be written as w n by 2 of nk. Okay. So let's see that. You can see here I have explained that this is the first one which I explained. Now the second part, Wn of 2n plus 1 into k. They are exponential. When there is a summation here, it is product. Okay, so we can directly write this as Wn of 2nk into Wn of k. This already we know Wn of 2nk can be written as Wn by 2 of nk. But now our summation, you can see it has become like this. If you check the first summation, what is this equation? This equation looks like exactly like a DFT. Only thing is, instead of n, we have n by 2. So this is a n by 2 point DFT. And this one, if you see, is again an n by 2 point DFT, but it is an n by 2 point DFT of x2 of n into Wn of k. Within the n by 2 point DFT. This one, this term. Okay. So now we can write this as x1 of k plus Wnk of x2 of k. Okay. Where x1 of k is the n by 2 point DFT and x2 of k is again another n by 2 point DFT. Is that clear? So x of k, if we take n is equal to 8, let us take x of k is periodic with the period 8. x1 of k is periodic with the period 4. Okay. x2 of k is again periodic with the period 4. Is that clear? Now let's check the computational complexity of these terms. That is x1 of k and x2 of k. As I said, x1 of k is a 4-point DFT. So what will be the complexity of this one? Okay. Write it here. That is x of k is equal to x1 of k plus this is our expression. Okay. So what will be the computational complexity for this? The complexity is n square multiplications, n into n minus 1 additions. So for this one, that's what we are computing, x1 of k. Now its length has become n by 2. Okay, so n by 2 square. Now you can follow this side. It is n by 2 square. x1 of k matram. Okay, x2 of k same, n by 2 the whole square. Okay, and there is another multiplication here. You can see x2 of k into Wn of k. How many times will this multiplication go? It will go 8 times because, n times, because we need to find all the values of xk, 0 to n minus 1. Okay, so there will be If you have 8, n as 8, there will be 8 such computations you will have to do. That is x of 0, x of 1, and so on up to x of 8, 7, 8 values. Okay. So you need 8 more multiplications here into w of n of k. So totally, you can see that we need 2 times n by 2 square plus n. Okay, number of multiplications. Now, same way, number of additions in the irkum. For the first one, that is for x1 of k, you have n by 2 into n by 2 minus 1. Okay, same for x2 of k. And then you should notice that there is additional n number of additions here. So you can see 2 times n by 2 into n by 2 minus 1 plus n. Okay. Now let's compare this with the n point DFT. Let us take a value n is equal to 8. We already know for n is equal to 8, we have 64 multiplications. Okay, that is n square, and 56 additions n into n minus 1. Okay. Now let's do the same thing for this expression, x1 of k plus x2 of k into wn of k. So we take this expression, replace n with 8, okay, 4 square, 2 into 4 square plus 8. 40, the number is 40. Okay, this goes to 40. And if you evaluate this one, you will get 32. So one single decimation, if you see, you have reduced the number of multiplications from 64 to 56, and then number of number of multiplications from 64 to 40, and then number of additions from 56 to 32. That is quite some reduction, right? Now this decimation can be further, you can further decimate the sequence. First you are decimating the given sequence into the even part and the odd part. Okay. Now you can further decimate this, the even of the even part, okay, and the odd of the even part. This again can be decimated as the even of the odd and the odd of the odd. Like this, you can go on decimating until it becomes 2. Okay. So your n point DFT becomes n by 2 point DFT, then it becomes n by 4 point DFT, then it becomes n by 8 DFT, and so on. If you are going to use 8 point, then it will be divided into 2 4 points, and then again into 2 points. Okay. With that, it will end. If you have 16, then it becomes 2 8, then 4 4s, and then 2s, like that. So now how do you get back the original sequence? So before that, you should know that as your spectrum has a symmetry, x of k has a symmetry, or it is, let us say, x of k plus n. Same way, x1 of k will be periodic with the period n by 2, and so on. And this w also has a symmetry. It has a conjugate symmetry. So we can write w n by 2 of n of k plus n by 2 will be minus w n of k. You can substitute and check that. It's in a conjugate symmetry. So once you get all the x1 of case and x2 of case, how do we combine for a 8 point? So x of 0 is x1 of 0, that is the 4 out of the 4 values. Okay, this is the case for n is equal to 8. So you have x1 of 0, x1 of 1, x1 of 2, and x1 of 3. As well as you have x2 of 0, x2 of 1, x2 of 2, x2 of 3. Instead of, what we want is x of 0, x of 1, x of 2, and so on up to x of 7. ഇതാണ് നമുക്ക് വേണ്ടത്. But we are having these two. Okay. So we are combining them. The first 4 values can be easily obtained using the original equation here. So x of 0 will be x1 of 0 plus w8 of 0 into x2 of 0. And x3 vara namukku ingane ezhudam. The moment x4 comes, you can see that this, because of the conjugate symmetry of w, it becomes a negative sign. So it is subtraction after that. x1 of 4 is the same as x1 of 0. അതുകൊണ്ടാണ് അവിടെ x1 of 0 എഴുതിയിരിക്കുന്നത് ഇവിടെ. It is actually periodic with the period 4. x2 of 0 is the same as x2 of 4. Okay, so the lower half will be subtraction. So this way we can, with whatever 4 values you have got for x1 of k and x2 of k, we can combine them and get all the x k's, 8 values of x k's. Pictorially, you can see the entire operation can be shown like this. You can see all the even values. We have collected all the even values. That is the 2 summations which we did there. And this odd values, okay, so these even values, you compute a 4-point DFT. You get all these x1, x1s here. These are the odd values, and you can see you get the values of x2 after computing the 4-point DFT. Then we are multiplying with w8 of 0, w8 of 1, w8 of 2, and w8 of 3. The upper, these indicate additions, okay? These indicate additions. Each node indicate addition. In fact, all the nodes indicate addition. And here you can see a multiplier. An arrow pointer indicates a multiplier. Here the multiplier is -1. So, and this is addition. This is addition. So you can see it is actually subtraction. Okay. So here at this point, x1 of 0 plus x2 of 0 into w8 of 0. So this point is the addition of this line and then this line. Like that, the upper half is all addition, lower half is all subtraction. Okay. Now the next stage is to decompose this into 2-point DFTs. As I said, you can further divide the even of the even and the odd of the even. The even of the even is 0 and 4. The odd is 2 and 6. Okay, so you can ignore these equations. We can go back to the second stage. You can see here I have decomposed the 4-point DFT into 2-point DFTs. And the procedure is very similar. Instead of a 4-point DFT, you will get two 2-point DFTs, which you can combine with addition and subtraction. Okay, the upper half, these two are additions and these two will be subtractions. Okay. So before subtracting, you multiply with this. Before adding or subtracting, you multiply with the W's. Then do this. The next level will be to decompose this 2-point DFT. We already know the W matrix of a 2-point DFT is 1, 1, 1 minus 1. This is nothing but one addition and one subtraction. Okay. So you can see here, this is the 2-point DFT. This is an addition. This is a subtraction. One addition, one subtraction. And you can see here, this is 0, 4, 2, 6, 1, 5, 3, 7. This is the even of the even. And this one is the even of the odd. Okay. So here, if you see, these are the final DFT of 8-point DFT of the given 8-point sequence, which if you plot x of k versus k, you get the spectrum. Okay. Or if you want to perform convolution, you can find y of k in the same way and then multiply x of k into, sorry, h of k and find out the inverse of y of k to get y of n, IDFT. Okay, Dana, we are supposed to do for this decimation in time FFT algorithm. So I will show one example of a problem now. You just observe it, watch it, and we'll do that in the next class, that is tomorrow, in the classroom. Okay. Now, computational complexity of this FFT algorithm. We have reduced it, right? From 8-point, we reduced to 4-point, then we reduced it to 4 2-points. The combination of all these together. So this is called as a butterfly. One unit of the computation. One addition, one subtraction, and a multiplication. In this figure, you can see here, this is 1, this is 1, this is 1, this is 1. That is 4 single butterflies are there. And you can see here also there is 2 overlapping butterflies. Here also 2 overlapping. Here 4 butterflies are overlapping. Okay. So one addition, one subtraction. Second. Okay. So totally we have 12 butterflies, so 24 additions and 12 multiplications. Okay. Mathematically, we can write the number of additions as n log n base 2 and the number of multiplications as half of that. Okay, n log base 2 n divided by 2. Now the speed, how fast is this FFT compared to the normal computation of DFT? So you can see here, when n is 2, 4, 8, 16, case of DFT, for a 16 point, you need 256 multiplications, and case of FFT, you need only 32. Same way for number of additions, you can see 240 additions are needed for computing a 16 point, whereas we need only 64 additions for FFT. Okay. So let's do this problem here. You are asked to compute the 8-point DFT of a sequence using decimation in time FFT algorithm. If you are asked to do using decimation in time, you use only decimation in time. If nothing is mentioned, you can either use DIT or DIF. Okay. So before, if you are given a sequence like this, the first thing you can do is you can write their sample numbers. Okay. Like this is the 0th sample, first sample, second sample, like that. Then you can properly put them in the algorithm. So you can see here I have written it. X of 0 is half, X of 1 is half, like that. Okay. The 7th sample is 0. And we need to have all the W values. Like for 4-point W matrix, we know, right? Same way, we can keep all the W's before the start of the computation. You already know that W is e to the power of minus j 2 pi by 8 in this case. Okay, into nk. So W8 of 0 is 1. We don't need all the W's, we need only half. Okay, W8 of 1 is 1 by root 2 into 1 minus j. W8 of 2 is minus j. 3 is minus 1 by root 2 minus j by root 2. So you can memorize these W values because it will be time consuming if you are going to calculate it in your exam hall. So remember these W values. Okay. And you can see the first value, that is half, is X of 0. Then this is the 4th value. 1, 2, 3, 4. 4th value is 0. Okay. Then the next one is first, this is X of 0, X of 4, this is X of 2, X of 6, like this. We need to pick from here all the values and drop it there in the scheme. See, this whole scheme is needed to do the problem. So you need to learn to draw this scheme correctly. And I will do that tomorrow in the class. Okay. And this is 1, 5, 3, and 7. Okay. Now you can see here, how did I get these values here? This is half plus 0 is half. Okay. Then the lower half is half minus 0 is again half. So I get similar values here. Half plus 0, half, half minus 0, half. So lower half is also the same way. The next stage, before going to the next stage, you need to multiply this with 1 and this with minus j before doing the addition and subtraction. Okay, so what will be the value here? Half plus half, which will be 1. Here it is half into minus j by 2. Okay, half minus j by 2. You can see the next value is half minus half 0, half, there is one more minus coming into picture, minus j into minus 1, it becomes half plus j by 2. Okay, here also, whenever you compute, this is a 4-point DFT. So you can see these two are conjugates. Okay. Here in the lower half also, you have 1, then half minus j by 2, 0, half plus j by 2. And this is the W. The first one is 1. The second one is 1 by root 2 minus j by root 2. Third one is minus j. Fourth one is this. After this, you have a major combination. Okay. These are all additions, the top ones. You add, you get 2 here. And the rest of the values will follow. Okay. Here you can see these two are conjugates, as I said, for any DFT. If they were complex numbers, they will also be conjugates. And same way here also, the next one. So conjugate. So we find the DFT using decimation in time FFT scheme. Okay. After computing the DFT, you can take it and write it down like this properly. If you are very good in computation, you can save time. You can do only the first 5 values. The rest of the values you can have it as a conjugate. So this classwork we will do tomorrow. Okay. Then let's do decimation in frequency. Okay. The next one. It's only 10:27.
ആര്
എന്താ മീൻ
ഒന്നുമില്ല സോറി.
Okay, can you see the slide? And part the slide ഇട്ടിട്ടുണ്ട്. Okay. So decimation in frequency. See, both are similar algorithms. Just a theory matra or a difference. One we are decimating in the time domain. The other one gets decimated in the frequency domain. That means even anomalous. We are transforming x of n to x of k. Okay. Both algorithms are doing the same thing. But idile namala decimation in time if you see the input side of the FFT algorithm, ipo idanengil FFT block nu paranjal you have x of k's here, right? X of n's here. Here you have the even, odd, like that. Okay, every second sample will be on the top, every even part, like that. But decimation in frequency la difference nu vechala, the output side, where the x of k's which we are finding, they will be decimated. So you will have the even on the top. Okay, x of 0, x of 2, x of 4, like that, that will be on the top, and the odd will be at the bottom. Every even sample will be chosen first. Otherwise, the algorithm is the same. Okay, same and parnal endana, I don't mean that the computation is the same, but the outcome is the same. Okay, decimation in frequency FFT algorithm. ആരെങ്കിലും സംസാരിക്കുന്നവരെ ഒന്ന് മൈക്ക് മ്യൂട്ട് ചെയ്തിട്ട് സംസാരിക്കും. ഓക്കെ, so now how do we do this, derive this algorithm? In the last case, you remember we divided that summation into two parts. One was the even part and the other one was the odd part. Here it is very simple. You simply divide the sequence into two halves. Okay, so adhiga explanation ivida avashyamilla. We have already seen how the summation is split into two halves. So you here simply divide the summation into two parts. That is, first n by 2 points as one summation, second n by 2 point as another summation. Okay, and we'll call the first half of the sequence as x1, the second half of the sequence as x2 of n. Okay, so suppose you have x of 0, x of 1 up to x of 7. We collect the first half, x1, x2 and x3 as the first summation, plus the second one, x4, 5, 6, 7. Okay, so first part ine nammal x1 nu vilikum, second part ne nammal x2 nu vilikum. Okay, rendu sequence aayittu we divide it into two equal halves, and then we find the DFT like this. DFT of the first part plus the DFT of the second part. Okay, so mathematically, we are, you can see here, the first summation goes from 0 to n by 2 minus 1. Second summation goes from n by 2 to n minus 1. Okay, first half, second half. That's the difference. Now, the first half is okay. The second half, the summation starts from n by 2. So we want to make it as 0, start from 0. 0 to n by 2 minus 1. So we can write it as n plus n by 2. Okay, inside the argument of x, and same way where this n also should be replaced by n plus n by 2. Now we can call this as x1 of n and this as x2 of n. Okay, so we rewrite this as x1 of n and this as x2 of n. Now what we are going to do is, we are going to explore how the even samples of the spectrum are going to look like and how the odd samples of the spectrum are going to look like. See, to find out the even parts of the spectrum, wherever we have a k, we can replace it by 2k. And for the odd part, we can replace it with 2k plus 1. Okay. So before that, I have written the same things before replacing with 2k. Only thing is, I have simplified this Wn of n plus n by 2 and Wn of n into Wn of n by 2 into k. Same, just the product. Okay. Now we are going to replace k by 2k. Wherever you have a k, you replace it with 2k. Okay, so here, when you replace with 2k, this became Wn of 2nk, became Wn of 2nk, and this became Wn of n by 2 into 2k. We already know that Wn of 2nk can be written as W n by 2 of nk. Okay. So n by 2 of nk. And this one becomes Wn of nk, which is actually 1. So that leaves, okay. So if you divide the sequence into two halves, then you can see that the even samples are nothing but the n by 2 point DFT of the first half plus the n by 2 point DFT of the second half. Okay, slightly different from the previous case. So the random same summation, we can combine them like this. Okay, x1 of, we can add x1 of n and x2 of n, and then take an n by 2 point DFT to get the even samples. Yes. Now let's examine the odd. For odd one, odd one you will also get a similar expression where this will end up in a subtraction. Okay, odd one. So let's replace wherever we had a k, we'll replace it with 2k plus 1. 2k plus 1. 2k plus 1. Now this you split it up. Okay, Wn of 2k into Wn of n. Same way, this Wn of 2nk can be written as Wn by 2 of nk. Okay. Adutha. Here, this one we already simplified here. This one is what is shown here. See that you get a Wn of nk. That's 1 ആണ്. Okay, ഇതും നമ്മൾ already last case ൽ ചെയ്തതാണ്. And Wn of n by 2 is nothing but minus 1. So you can see our expression becomes a subtraction because of this conjugate symmetry. You get a minus sign here. Now you can combine them together. You can see x1 of n minus x2 of n. Each term common. So you can combine them like this. x2k plus 1 will be equal to x. It's like as if you subtract the sequences, multiply it with Wn of n, and then take a n by 2 point DFT. Okay. So these are the two cases we have seen. Now pictorially, we can see the combination. Same way we can further go on like that. Okay. You divide the sequence into two halves, add the first one, add the both to get the even parts, subtract both to get the odd parts. Further, you can divide it into two. Again, addition, subtraction, like that it goes. Okay. So it is like this. If you want to find a 8-point DFT, this 8-point DFT the pictorial representation. So you can see here we have simply divided the first half and the second half of the sequence. Then you are adding it here. This x of 0 plus x of 4 either at this point. Okay. Here x of 1 plus x of 5, x of 2 plus x of 6, like that. And at this point you are subtracting x of 0 minus x of 4 and so on. And before taking the 4-point DFT, we are multiplying with the W's, W8 of 0, 1, 2, 3. and then you take a 4-point DFT, two 4-point DFTs, and at the output of the 4-point DFT, you can see you got all the even parts on the first 4-point DFT, and these are the odd parts of the spectrum. In the same way, these four things can be again divided into two halves, okay, and you can decompose it into 4. Here, not at this point. Before going to the 4-point DFT, you can divide this into two 2-point DFTs. So before getting into a 2-point DFT, you will add, okay, the lower half and the upper half. You will add like this, subtract like this, okay, subtraction like that, and then do the next one like this. So this is the whole scheme. After that, you have the 2-point W. You can see one addition and one subtraction. Okay. And if you see the outputs, you can see the even of the even part of the spectrum, odd part of the spectrum, that is XE of K, will be on the top. Okay. The odd part of the even spectrum, adinte thaazhe varunu. This is the even part of the odd. The difference between the decimation in time and decimation in frequency is it's like exactly opposite. In the time case, you rearrange all the input samples into a particular order, and then the spectrum will be in order. But in this case, for the decimation in frequency, the input side, if you see, they are all in order, and the output side is rearranged or decimated. Okay. Computational complexity will be the same, because the same number of multiplications, same number of butterflies, same number of additions, everything. Okay. So if you see here, this problem also we'll do in the class. Right now I'll just show. We need to write the sample number 0, 1, 2, 3, and the W's have to be kept before the start of the computation. Okay. And then we need to draw the scheme. എല്ലാവരും ഈ scheme നോക്കി പഠിച്ചിട്ട് വരിക. ഇത് how the scheme is being drawn. Okay, I will tell you in the class how to legibly draw the scheme, and then we'll work the problem on the scheme. Okay. We have simply divided the sequence into two parts. The upper half is addition. So 1 plus 0 is 1. 1 plus 0 is 1, like that. And then 1 minus, this is 1 minus 1. Sorry, 1 minus 0 is again 1. 1 minus 0 is 1, like that. And then we multiply with the W's first. Okay. The higher level W, 0, 1, 2, 3. Then again you do the, here you do the addition. Only the lower half has the W's, okay? The upper half doesn't have. So this is 1 plus 1, 2. Then the next one is 1 plus 1, 2. The lower half, 1 minus 1 is 0. 1 minus 1 is again 0. Then you multiply with 1 and minus j. Here also, lower half you will multiply with 1 and minus j. You can see here multipliers. Multipliers in the kuda, you have the number with which you multiply. All these are multipliers. This is a multiplier. This is a multiplier. This is a multiplier. Okay, whenever we have multipliers, we have to show like that. In the size on them, other that because I made them different ways, they look different, but they are all the same multipliers. They are all multipliers. Okay. And here, if you see, the spectrum is coming in a different way. The samples of the spectrum are appearing in a different way, but a conjugate ingane irukkum. This is the DC component, and this is actually x of 0, this x of 4, x of 2, x of 6. Same way, this is x of 1, x of 5, x of 3, x of 7. So after doing the problem, you have to rearrange them. Okay, rearrange them like this. Can you see? I have rearranged them. The 4, 0, 0 is here. You have to put them in the proper place, and then only you have to present your spectrum. Otherwise, it is wrong. Then you can cross check for your conjugate symmetry. Okay. So this we'll see in the next class. Yes, sometimes if there is more holidays, then we'll have a combined class. I will call for the attendance now. Give me a moment, I will take a pen and come. ആൾക്കാർ വന്ന് പോകുന്നത് ഞാനിവിടെ ടൈം നോട്ട് ചെയ്ത് വെച്ചിട്ടുണ്ട്. ഓക്കെ, സോ only people who have been here for ഈ മെസ്സേജസ് ഒന്നും ഞാൻ ഓൾറെഡി കണ്ടിട്ടില്ല. ഓക്കെ, when you are in one window, you don't see the other window. If anybody is there from the A batch, you can leave. The B batch students alone can hear. Mic unmute ചെയ്തിട്ട് പറയൂ. Okay. Joel John.
Present.
John Zubin.
Present, miss.
എവിടെയാ John Zubin?
ഞാൻ റൂമിലാ.
തബ്ഷീർ അലി ആണല്ലോ അവിടെ കാണിക്കുന്നത്.
ഒരേ ഡിവൈസ്
ഒരേ ഡിവൈസിൽ നോക്കുന്നുണ്ടോ? അതെങ്ങനെയാ ഈ മൊബൈൽ ഒന്ന് കാണിക്കോ? അത്
ക്യാമറ ഓൺ ആയ?
ക്യാമറ ഓൺ ചെയ്യൂ. സമയം പോവുകയാണ്. ഓക്കെ, ജൂലിയ ഓഫ് ചെയ്തോ ക്യാമറ? പിന്നെ ഓക്കെ, ജൂലിയ ഒരു ഓക്കെ. ജൂലിയ. അനന്യ.
Present, ma'am.
കണ്ണൻ.
Present, ma'am.
കരീന.
Present, ma'am.
Okay. കാസിനാഥ്.
Present, ma'am.
കിരൺ.
Present, miss. Present.
ഓക്കെ. നസീബ്.
Present, miss.
പ്രസന്റ് പറഞ്ഞവരെല്ലാം പോകാം. ഓക്കെ. മഡോണ.
Present, ma'am.
മനസ്.
Present, ma'am.
നിസാബ്.
Present, ma'am.
മുഹമ്മദ് അമീൻ. എല്ലാരും ഒന്നും അത് ക്യാമറയെ ഓൺ ചെയ്തിട്ട് പ്രസന്റ് പറയൂ. ഓക്കെ. Amin.
Present, ma'am.
Okay. Muhammad Hassan. Absent. Ramin. Absent. Shahzad.
Present, ma'am.
ഇവിടെ മൈക്ക് ക്യാമറ ഓൺ ചെയ്യണം എന്ന് പറഞ്ഞിട്ടുണ്ട്. ഓക്കെ. തബ്ഷീർ.
Present, miss.
യെസ് യെസ്. റൈഹാൻ.
Present, miss.
നവീൻ ആബ്സെന്റ്. നവീൻ എവിടെ? നീരജ്.
Present, ma'am.
ഓക്കെ. നിരഞ്ജൻ.
Present, ma'am.
ഓക്കെ. നിവേദ് ആബ്സെന്റ് അല്ലേ? നോയൽ.
Present, ma'am.
ഓക്കെ നോയൽ. പാർത്ഥിപൻ സി കെ. പാർത്ഥിപൻ എവിടെ? പാർത്ഥിപൻ ഇല്ലേ? ആബ്സെന്റ് അല്ലേ? ഓക്കെ. പ്രണവ്. പ്രണവ് ഗോപി.
Present.
ഓക്കെ. പ്രണവ് പി.
Miss present.
പ്രിൻസ്.
Present, ma'am.
മൈക്ക് ഒന്ന് മ്യൂട്ട് ചെയ്യൂ. ഓക്കെ. പുണ്യ.
Yes.
പുണ്യ ആബ്സെന്റ്. രാഹുൽ.
Present, ma'am.
ഓക്കെ. ഋഷഭ് ദേവ്.
Present, ma'am.
സഞ്ജന.
Present, ma'am.
സഞ്ജയ് കൃഷ്ണ.
Ma'am.
ഓക്കെ. എവിടെയാ സഞ്ജയ് കൃഷ്ണ? സഞ്ജയ് കൃഷ്ണ.
Present, ma'am.
സൗരഭ്.
Ma'am.
ഓക്കെ സൗരഭ്. സവാദ്.
Present, ma'am.
എന്താ സവാദ്, പഠിച്ചോ?
എന്ത് മിസ്സാ?
പഠിച്ചോ?
ചിരിക്കല്ല.
പഠിച്ചില്ലേ? ആ ഓക്കെ. ഷോമിയ.
Present, ma'am.
ഓക്കെ. സിബിൻ രാജ്. സിബിൻ രാജ് ആബ്സെന്റ്. സിദ്ധാർത്ഥ്.
Present, ma'am.
ഓക്കെ. സൂര്യജിത്ത്.
Present, ma'am.
ഓക്കെ ശരി. സൗരവ്.
Present, miss.
ഓക്കെ. ശ്രീദേവിക.
Present, ma'am.
ഓക്കെ. ഗോവർദ്ധൻ. ഗോവർദ്ധൻ ആബ്സെന്റ്. തമന്ന.
Present, miss.
ഓക്കെ. തസ്ബിഹ. തസ്ബിഹ ആബ്സെന്റ്. തസ്ബിഹ ഉണ്ടോ? ഇല്ല. Vaishnav.
Present, Miss.
Okay. Vandana.
Present, Miss.
Vinaya.
Present, Miss.
Vismaya.
Present, ma'am.
Okay. Vrinda.
Present, Miss.
Okay. Akshay. Akshay absent. Abdul. Aslam. എവിടെയാ മുഹമ്മദ് അസ്ലാം? അസ്ലാം. മുഹമ്മദ് അസ്ലാം എവിടെ? ആബ്സെന്റ്. മുഹമ്മദ് അസ്ലാം ആബ്സെന്റ്. മുഹമ്മദ് ഷാദിൻ
Present.
എവിടെ? ഓക്കെ. സായം എവിടെയായിരിക്കുന്നു? സാദിൻ സോറി സായന്ത് എവിടെ? ഇങ്ങനെ ഈ ഫേസ് ഒന്നും കാണിക്കാത്തവർക്ക് അറ്റൻഡൻസ് ഇല്ല. ഓക്കെ, ഇത് സായന്താണോ? ഇത് മുഹമ്മദ് സായന്ത് എവിടെ? എല്ലാം പ്രസന്നസ് പറയും, ഇവിടെ ആള് കാണുന്നില്ല. ശ്രീലക്ഷ്മി.
Present, Miss.
ഓക്കെ. സായന്ത് എം
Ma'am.
ഓക്കെ. ഇനി എന്താണ് വേറെ പ്രശ്നമുള്ളവരെ? ആരാ? ശ്രുതി.
വിളിച്ചില്ല, ma'am.
ശ്രുതി ഉണ്ട്. ഓക്കെ, ഇനി എല്ലാരും പോകാം. ഐസോ ശ്രുതി. മുഹമ്മദ് ഷാൻ. ആ നവീൻ എവിടെ പോയി? ഓക്കെ. ഓക്കെ, യു ക്യാൻ ലീവ്.